let us discuss about the evaluation of improper integrals. Now, let us consider improper integrals of the form integral from minus infinity to infinity f of x dx. Now, we can denote this improper integral as the sum of two limiting integrals, like limit a tends to infinity minus a to 0 f of x dx plus limit b tends to infinity integral from 0 to b f of x dx. If both limit exist, integral minus infinity to infinity f of x dx equal to limit r tends to infinity integral from minus r to r f of ax dx. This limit is called the Cauchy's principal value of the integral. That is principal value integral minus infinity to infinity f of x dx. Okay, thus we have closed integral over c f of z dz equal to integral over s f of z dz plus integral minus r to r f of x dx, and it is same as 2 pi I sigma residue of the function f of z. Therefore, we have integral from minus r to r f of x dx equal to 2 pi I sigma residue of f of z minus integral over s f of z dz. Now we can draw that now. This is like this. Here we can draw the x-axis, y-axis. Now we can consider the arc S, and here it is minus r, it is plus r. Okay, so we have integral minus infinity to infinity f of x dx is same as 2 pi I sigma residue of f of z. Okay, now let us move to one problem now. Okay, the first question is, show that integral from 0 to infinity dx divided by 1 plus x raised to 4 equal to pi divided by 2 root 2. So here we are considering the given question in complex form, dz divided by 1 plus z raised to 4. Here we have f of z is 1 by 1 plus z raised to 4, and we know the singularities are obtained by equating the denominator to 0. So here the poles are obtained by equating the denominator to 0. So 1 plus z raised to 4 equal to 0. Thus we have z raised to 4 is equal to minus 1, and it is same as cos pi plus I sin pi. Now we can generalize this as z raised to 4 is equal to cos pi plus 2k pi plus I sin pi plus 2k pi. Now we can apply our de Moivre's theorems. Therefore we have set this equal to cos pi plus 2k pi divided by 4 plus I sin pi plus 2k pi divided by 4, and here k takes the values 0, 1, 2 and 3. Now we can represent this in the exponential form e raised to I theta model. So e raised to I into pi plus 2k pi divided by 4, where k takes the values 0, 1, 2 and 3. Now when k is equal to 0, we have the value of z is e raised to I pi divided by 4, and when k is equal to 1, e raised to 3I pi by 4, and when k is equal to 2, e raised to I 5 pi by 4, and e raised to I 7 pi by 4. Okay, here we can see that these two lies in the upper half plane. Okay, lies in the upper half plane, and whereas here we have e raised to 5I pi by 4, and that is same as e raised to minus I pi by 4, and this one is same as e raised to minus I 3 pi by 4. Now we can see that these two singularities lies in the lower half plane. Now we can calculate the residues in the upper half plane. So at first we can calculate the residue of our function at z is equal to e raised to I pi by 4, and so this is equal to limit z tends to e raised to I pi by 4. Our function is 1 by 1 plus z raised to 4, and this is of the form p of z by q of z. So it is equal to 1 by numerator divided by derivative of the denominator at z is equal to e raised to I pi by 4, and its value is e raised to minus 3I pi by 4 divided by 4, and that is same as minus 1 by 4 e raised to I pi by 4. Similarly, we can calculate the residue of the function f of z, that is z is equal to e raised to I 3 pi by 4, and it is equal to limit z tends to e raised to I 3 pi by 4, 1 by 1 plus z raised to 4. Now this is equal to 1 by 4 z cube at z equal to e raised to I 3 pi by 4, and that is equal to 1 by 4 into e raised to minus I 9 pi by 4, and its value is 1 by 4 e raised to minus I pi by 4. Thus we have the residues in the upper half plane. Now we can calculate the required integral now. Therefore, integral minus infinity to infinity dx divided by 1 plus x raised to 4 equal to 2 pi I into sum of residues. Here we have minus 1 by 4 e raised to I pi by 4 minus the last value is 1 by 4 e raised to minus I pi by 4. Now you can take that minus 1 by 4. Here we have plus minus 1 by 4 outside. So minus 1 by 4 2 pi I e raised to I pi by 4 minus e raised to minus I pi by 4. Okay, and we know sin theta equal to e raised to I theta minus e raised to minus I theta divided by 2i. Now we can apply that formula here. So here we have this is minus pi I divided by 2i sin pi by 4. And we can cancel these 2 then I into I square minus 1. So here we have pi into sin pi by 4 and sin pi by 4 is 1 by root 2. Thus we have the answer is pi by root 2. Therefore integral from 0 to infinity dx divided by 1 plus x raised to 4 is equal to 1 by 2 times integral minus infinity to infinity dx divided by 1 plus x raised to 4, because the function 1 by x raised to 4 is an even function. So this is equal to pi by 2 root 2. So this is our required answer. Okay. Here we use the following assumptions. F of x is a real rational function whose denominator is not equal to 0 for all real values of x and is of degree at least 2 units higher than the degree of the numerator. Okay, so the degree of the denominator always larger. And its degree is at least 2 units higher than the degree of the numerator. Okay. Now we can move to the Fourier integrals now. Here integral minus infinity to infinity f of x into cos sx dx and integral minus infinity to infinity f of x into sin sx dx. Here s is real. Okay, here integral minus infinity to infinity f of x into e raised to I sx dx is equal to 2 pi I into sum of the real part of f of z into e raised to sorry, we can cut that. Now let us consider. Okay. Now we can consider the Fourier integrals. Integral minus infinity to infinity f of x cos sx dx and integral minus infinity to infinity f of x sin sx dx, where s is real. Integral minus infinity to infinity f of x into e raised to I sx dx is equal to 2 pi I into sum of residues of the function f of z into e raised to I s z, where s is greater than 0. Where we consider the poles in the upper half plane for calculating the residues, then equating the real and imaginary parts. When we equating the imaginary part, we have integral minus infinity to infinity f of x into cos sx dx equal to minus 2 pi sigma imaginary part of the residues of the function f of z e raised to I s z, where s is greater than 0. And similarly, integral from minus infinity to infinity f of x into sin sx dx equal to 2 pi summation the real part of residues of the function f of z e raised to I s z. Okay, where s is greater than 0. Now let us move to an application of this result now. So the question is, evaluate integral minus infinity to infinity cos sx divided by k square plus x square dx. Or we can write the same question as show that integral from minus infinity to infinity cos sx dx by x square plus k square plus x square is equal to pi by k e raised to minus k by s. And similarly, integral minus infinity to infinity sin sx divided by k square plus x square dx equal to 0. Here s greater than 0, k greater than 0. So we have to prove these two results. Okay. So let us consider integral minus infinity to infinity e raised to I s z dz divided by k square plus z square. And here we can consider our f of z as 1 by k square plus z square. And so the poles are obtained by equating the denominator to 0. Thus we have z square equal to minus k square. So z is equal to plus or minus ik. And here we have z is equal to ik lies in the upper half plane and z equal to minus ik lies in the lower half plane. And here these are simple poles also. So let us consider the residues in the upper half plane only. So residue of z at ik, our function is, here we are considering f of z into e raised to is z. So this is equal to residue z equal to e raised to z equal to ik. Now our function e raised to is z divided by k square plus z square, and this is of the form p of z by q of z. So in order to find the residue, we can consider the numerator divided by derivative of the denominator at the point z is equal to ik. And that value is e raised to minus ks divided by 2ik. Okay. Therefore, we have integral minus infinity to infinity e raised to sx dx divided by k square plus x square equal to 2 pi I into sum of residue. Here we have the residue is e raised to minus ks divided by 2ik. So the answer is pi by k e raised to minus ks. Okay. Therefore, integral from minus infinity to infinity cos sx dx divided by k square plus x square equal to, we have to consider the real part only, that is pi by k e raised to minus ks. Similarly, we have integral minus infinity to infinity sin sx dx divided by k square plus x square equal to 0. That means here we are equating the imaginary part of this answer. Okay, thus we have the required answer. Now let us move to another problem now. The question is, evaluate integral 0 to infinity dx divided by 1 plus x square all raised to 2. Okay, here we can see that the function 1 by 1 plus x square whole square is an even function. So we can write this is same as 1 by 2 integral minus infinity to infinity dx divided by 1 plus x square the whole square. Okay, Now here we can consider the question in the complex form, and the poles are given by equating the denominator to 0. That means 1 plus z square, the whole square is equal to 0, and here we have z square equal to minus 1 twice. So z is equal to plus or minus I. So this is a pole of order 2. Pole of order 2. And here we can see that z equal to I lies in the upper half plane. So we have to calculate the residue at that point. Okay, so we have the residue of our function at z is equal to I is equal to 1 by 2 minus 1 factorial limit z tends to I d by dz of z minus I square into f of z, and here we have f of z is z plus I the whole square into z minus I the whole square. So we can cancel these two terms, and after that we can take the derivative of the function 1 by z plus I the whole square. So we have that is equal to limit z tends to I minus 2 divided by z plus I whole raised to 3, and that is equal to minus 2 divided by 2I whole raised to 3. So we have its value is equal to minus 2 divided by 8I square, 8I cube. I cube means I square into I, and I square is minus 1. So here we have minus I. So we can cancel that minus and minus. So the answer is 1 by 4I. Thus we have the required answer is 1 by 2 into, now 2 pi I into sum of residues of the function f of z. That is our formula. Okay, so that is equal to 1 by 2 into 2 pi I into 1 by 4I. So here we have 2 cancel, I cancel. So the answer is pi divided by 4. Okay, so this is our required answer. Now let us move to one more problem now, similar type of. Okay, that question is evaluate integral from minus infinity to infinity 1 by 1 plus x square whole raised to 3 dx. It's a very important question. So here also you can see that z square is equal to minus 1 thrice. So z equal to plus or minus I is a pole of order 3. Now you can calculate the residue in the upper half plane only. So it is a pole of order 3. So here we have 1 by 3 minus 1 factorial, that is 1 by 2 factorial limit z tends to I d square z by dz square we have d square by dz square of our function z minus I raised to 3 into f of z, that is 1 by z minus I raised to 3 into z plus I raised to 3. So we can cancel this. After that we can take the derivative of this function twice. So this is d by dz of minus 3 divided by z plus I raised to 4. Now let us take the derivative again. So that is limit z tends to I 12 divided by z plus I raised to 5. Now we can substitute z is equal to I. So that is equal to 6 divided by 32 I raised to 5. Okay, so this is 3 by 16 I. Now let us move to our required question now. Here we have to find integral from minus infinity to infinity. So the formula is 2 pi I into sum of residues of the function. So this is 2 pi I into, what is the residue here? 3 by 16I. Okay, so that is equal to 3 pi divided by 8. Okay, now let us stop now. Thank you all.